In this video, we're going to simulate a Swiss lever escapement mechanism. After watching this video, you'll understand how you can build this model completely from scratch inside ProtoTwin. The process for creating any model in ProtoTwin always begins by importing the CAD for your mechanism, machine, or robot directly into the simulation environment. Once the CAD has been successfully imported, you can now begin to add components to the specified parts. To select an entity from a subassembly, you can control right-click, then select the entity for the balance wheel assembly. I'll now add a physics component to this entity and then set the collider to none, since we'll be adding collision geometry to other parts. Next, we'll create a joint and then set the constraint type to revolute. I can then configure the axis for the joint and the anchor point by selecting appropriate features from the CAD. I'll then add a spring to the balance wheel assembly and then select the joint we just created and configure the stiffness coefficient for the spring to be 0.1. We now need to add collision geometry for the various parts. I'll first select the balance wheel, then add a physics component to this entity and set the body type to attached. Attached specifies that the entity should have no rigid body, but that its collider should be attached to the rigid body of the nearest ancestor entity, which of course is the balance wheel assembly. I'll then select the impulse pin underneath the balance wheel, which is this red part you see here. I'll then add a physics component again and set the body type to attached, which will attach the collider to its parent. With the physics now correctly configured for the balance wheel, we need to begin configuring the physics for the lever assembly. I'll use Control right-click to select the lever assembly again, then add a physics component with the collider set to none. I'll then add a joint, set the constraint type to revolute again, then select the axis and anchor properties, which will allow the lever to rotate about the anchor and around the specified axis. To test the physics, we can run the simulation and swap to navigate mode. We can then click and drag to rotate the lever, and likewise for the balance wheel. Notice how the balance wheel oscillates because of the spring we added. Okay, great. I'll reset the simulation and then swap back to edit mode. We can now set up the colliders for each of the children. I'll select the red stone entity, then add a physics component, just like we did for the children of the balance wheel assembly. For the red stone, notice how the graphics mesh geometry is convex, meaning there are no holes in the mesh, and for any 2 points in the domain, all points on a line that connect these 2 points are also in the domain. This tells us the convex collider is suitable here, which we can inspect by enabling the physics visualization mode in the info bar at the bottom of the viewport. Remember, we need to set up the body type to attached, which will attach the collider to the rigid body of the parent. Similarly, for the second stone, we'll add a physics component again and set the body type to attached as well. Finally, I'll select the Swiss lever entity, but now notice that the graphics mesh geometry is highly non-convex, since there are holes and also because there are points that aren't inside the domain for a line connecting 2 points inside the domain. Hence why, for this entity, it makes sense to generate a custom collider. ProtoTwin will then automatically upload the graphics mesh and download the graphics mesh into the custom collider tool. I will now generate a multi-convex collider. Notice how the convex hulls don't exactly represent the shape well enough, though. For this mechanism, since we require precise collision detection, I'll set the collider to SDF and then generate a signed distance field collider. We can orient the view cube to determine whether the points are spaced well enough or not. I think this is good enough. I'll now click Save, which will upload the collider from the tool and download the collider back into the simulation environment. Next, we need to add physics to the red banking pins. Since these pins are grounded, I'll set the body to kinematic, which will ensure that both parts are not experienced by external forces. Finally, I'll select the wheel on the left and then add a physics component, which will be the last time we have to do this. Since the geometry is very highly non-convex, we want to generate a custom collider for this part. We'll choose the signed distance field collider again, just like we did previously, and then click the Save button to import the generated collider back into the main application. For this wheel, we need to add a revolute joint again and configure the axis and anchor properties by selecting appropriate features from the CAD. This will enable the wheel to rotate in the XZ plane around the anchor point we configured. Finally, I'll add a spring component to the wheel entity. For the spring, we want the spring to act on the revolute joint for the wheel, which we'll use to model tension, since in practice there will be tension. I'll set the stiffness coefficient to 0.002 and the rest offset to -3,600 degrees, which will determine the resting position of the wheel. I forgot one final thing. we need to lower the default friction coefficients from 0.6 to 0.2, which will reduce friction in the mechanism. I hope this video showed you how quick and easy it is to build a model like this, completely from scratch inside ProtoTwin.
Thanks for watching.